Hello everybody, this is the video clip for chapter 3 and we still talking about the applications of a derivative in terms of finding a local maximum and a local minimum. Okay, so let us recall a little bit, okay, what we have been doing. The first one, we're talking about the increasing and decreasing functions. Okay, so if you can solve the inequality f prime x greater than 0, and you can find like in which interval that this inequality holds, then it means that over that interval your function f is increasing. On the other hand, if your f prime is negative and you can solve this inequality into the interval x here, then you can determine that your f is a decreasing function over that interval I, okay, where your f prime is negative. And we have another definition, okay, saying that if you can solve for the x such that your derivative equals to 0, okay, so this means that you having the, again, the horizontal tangent, okay, so it can be either like this or it can either like that, okay. Actually it can be this one as well, okay, the tangent that it is horizontal, okay. Then that value c, okay, so don't forget that this one is the x value, okay. This x value c is called a critical number of a function f, okay. However, there is another kind of critical number, okay, so you can find it by looking at the c, okay, the x value c such that your f prime does not exist, okay. So it will be either the one that make your derivative equals to 0 or derivative at that point does not exist, okay. That will be your critical number, okay. And if it does not exist, then the thing will look like this one as a angle like this, okay, or it can be like that, or it can be like this, okay. And the thing that we may need to emphasize here is that the c, okay, the x value that you are talking about, okay, in order to make it as a critical number, it must be a number that originally it is inside a domain of a function. For example, if your function under consideration is look like 1 over x squared, then it means that your x cannot be 0 at the beginning, right? So it means that 0 can never, I mean, can have no chance to be your critical number of that function f at the beginning, okay. So the critical number, okay, must be the one that inside a domain f under consideration, okay. And please keep in mind again that this one, or the critical number, it just a candidate, okay. It is the or candidate to be uh, uh, I mean, so that your function will have a local max or a local min occur there, okay. So it just the candidate, okay, to achieve the local max or a local min at that point, okay. And by candidate, so it means that it can be either max or min, or it can be nothing, okay. For example, if your critical number look like that, it is not a hill or it's not a valley, right? So it's nothing. So it can be either local max, local min, or it can be, not that important point on your function, okay. So in order to determine whether the critical number that you obtain is either a max or a min, we have one way to do is the so-called a first derivative test, okay. So first of all, you need to find your critical number. So okay, as we told you, this is all candidate. And then you look at the sign of your f prime. If the sign of your f prime change from positive to negative, okay, at this point, so it means that you have a hill. So it means that at that point your fc is a local maximum value of a function. But if your f prime change from negative to positive, so it means that you have a valley. So the fc, okay, the value, the y value at this point, it will be a local minimum value, okay, of a function. And if we're talking about a local extremum, this is another terminology. The extremum, it can be either a local max or a local min. Okay, okay. So let us look at one more example about the local maximum or local minimum value. So for this one, your f, it is the x cubed, ax squared, and bx. Okay, and we say that this function f attain the local max. Okay, this is the value. Okay, and it attain at f at x equals to -1. Okay, so again, if it attain a local maximum here, okay, so it means that this one at the beginning, it has to be a candidate first, right? So it means that at this one, actually it is a critical, this one is one of the critical number, okay, of your function f. Okay, so how can you find the critical number? So it must be the one that your f prime either equals to 0 at that point or does not exist. So let's look at the f prime, which is 3x squared, 2ax, and then b. So again, this one exists for each and every x in a real number because it's just a polynomial, right? So it means that this critical, it must be the one that make your f prime equals to 0. So it means that at this point, okay, your f prime at -1 is 0. So this means that if you just plug in your x, okay, here and there to be -1, so we have this 2a -1 and b must be 0. So it means that you got a 3 and then minus 2a and plus b equals to 0, or it can be just 2a and b equals to -3, right? Okay, so now another thing is that, or you can just say that maybe this one maybe is a little bit better, 2a minus b equals to 3. Okay, this is one relation between a and b. So look at another one. It's saying that the value, okay, the maximum value. So the maximum value is actually a value of a function. Okay, so a max of a function f, it is 2, right? So it means that your f at some point will be equal to 2, right? So now at which point, okay, that the maximum achieved, so it is right now at -1, right? So here is another relation. So you just plug in your x here and there into -1. So you have -1 cube, okay, a and then -1 square, and then b with -1 equals to 2, right? So it means that you got a and minus b equals 2. This is a 2, this is another -1, so you have a 3, right? Okay, so here's another relation between a and b. So from here you can take a subtraction, right? So you end up with 1a equals to 0. So if your a equals to 0, then it means that your b must be -3, right? Okay, so this means that actually your function f, okay, it is in terms of x cubed and then minus 3x, okay, and it will attain a maximum value at this particular point. Okay, so you may need to considering this function by yourself a little bit again by saying that, hey, if this is your function, okay, then whether they have a local minimum or not, okay, if they have, if this function have the local minimum, where is the local minimum achieved, and what is the value of the local minimum value, okay, of this function, if it exists, okay. If it's not, then just say that it does not exist. Are we all right? Okay. So as we take a look at all this kind of example, it seems that the function under consideration has no end, right? Okay. So it's look like all the domain, okay, it seems to be like from negative infinity to infinity and all that kind of thing. However, if your function has a bounded domain, okay, so instead of looking at the whole real line, they just look at only on a bounded interval, okay, then how are we going to find the extreme value, okay, of that kind of function? So let's look at this one, the extreme value. And this kind of extreme value sometimes is called the absolute extremum or the global extremum, okay, depends on the book. So the theorem saying that if your f is continuous, so it must be continuous over the closed interval from a to b, then your f must attain an absolute maximum value and absolute minimum value on that closed interval. So you need to have like both of them. And this one just make a remark that the absolute max or min may be at the end point as well. Okay, so it can be at the end point or inside this interval. Okay, so it depends. Okay, depends on the problem. So for example, let's take a look at this graph. Okay, here is your A, there is your B. Okay, so if you take a quick look, this one is a hill. Okay, this one look like a valley. Okay. Okay, so what does this mean? This one a hill correspond to a local max. This one correspond to a local min. Okay. And if you really take a look, okay, do we have a function value that is larger or higher than this local max? We don't, right? This is the peak, the highest value of the function. So it means that this one is not only a local max, but it's also the absolute max as well. Over which interval? Over the closed interval from A to B. Okay. How about this one? Do we have any y value that is lower than this value? No, right? This is the lowest point. Okay, so it means that this one also correspond to what? To absolute, okay, minimum of this function over this closed interval from a to b as well. We okay? Okay, so this means that for this function, the absolute max and the absolute min occur, okay, at this point. Okay, let's say this is C1, this is C2, inside the interval from A to B. Okay, however, if you take a look at this one instead, here is a valley, there's a hill. Okay, this one is a local max, this one is a local min. However, do we have some other part or some other value, y value or a function value that's higher than this hill, this peak? Of course, it's right here, right? This one is higher, is larger than this local max. So this one is called the absolute maximum of this function f over the interval from a to b. Okay, here over the interval from a to b. And on the other hand, do we have some other part that's lower than this local min? Of course, right there, right? You see, so here is the absolute minimum of the function f over the interval from a to b. So it means that for this example, the absolute max or the absolute min, okay, you can find it, and it is attained at what, at the end point, okay, of the function. So, okay, oh sorry, of the interval, the end point of the interval, okay, under consideration. Are we all right? So it can be like that. So how are we going to find the absolute max or min? So we have the so-called the closed interval method. Okay, so the first one, you must find all critical points. Why is that? Or this peak can be a good candidate for your absolute max and min as well, right? Okay, so you need to find all critical points, but then you don't really need to do any test. Okay, all you need to do is a comparison. Okay, or the comparison. So number two is a comparison, a value of a function f at each critical point and also the end point. Okay, the end point of your interval a and b. So the largest value correspond to the absolute maximum, and the smallest value correspond to the absolute minimum already. Okay, so you don't really need to do any first derivative test or anything. Okay, the critical points as well as the two endpoints, okay, compare, then you can immediately determine which one is the absolute max and the absolute min. Okay, so for example, here's your a and b. Now first you find a critical, right? And you should know right now, to find a critical, you find a derivative first, which is negative 3x squared 12x, right? And then because this one is it is the polynomial again, so it will be exist for each and every x inside this closed interval. This time we don't talking about the all real number, because now we already restrict our problem into this closed interval negative 1 to 2. Okay, so you need to find the critical in the case that it is equal, your derivative equals to 0. So here we have this one. Okay, so you pull out the 3 and the x. All right, so you have a 4, is it? So it means that your x equals to 0 and 4. Okay, however, it must be the one that is contained in this interval. Are we all right? Okay, so this one is out. Okay, this 4 is not in negative 1 to 2. This one it is in, okay, the 0. So it means that we are not going to consider the one outside. Okay, only this one that we are going to consider. So which value that you need to compare? Okay, so you compare the critical. All right, you compare the endpoint. It's okay, you got two endpoints at negative 1 and 2. Okay, so you are going to find your function value over here. Okay, so for the first one, if your x is 0, this one is gone, this one is gone, so you have negative 5. Okay, for the next one, if your x is negative 1, so here is negative of negative 1 cube, and then 6 negative 1 square minus 5. So you have 1, and then 6, and then minus 5, which is 7 minus 5. So you have 2, right? Okay, a function value is 2. So if your x is 2, so you have negative 8, you have 6 and 4, which is 24, and then minus 5. Okay, so you have 24 minus 13. Okay, so it is 11, is it? Is that correct? Okay, so here is 11. So which one is the highest? Which one is the largest value? Here is the largest. So this one is already the absolute maximum value. Okay, is 11, and it occurs, so okay, at the point x equals to 2. But here is the smallest, right? So here is the absolute minimum value, and it is occur, okay, it's -5. It occurs at the point x equals to 0. Are we okay? So you need to really be careful about the function value and the place that the function value occur. Okay. So for this one, the next one you need to consider a square root 5 minus 4x over this closed interval from -1 to 1. Okay. So now you are going to find your f prime, which will be this one. Don't forget that it is a what 5 minus 4x raised to the power 1/2, right? So your f prime, it is what 1/2, and then 5 minus 4x raised to the power -1/2, and then a derivative of the inside. So you have -2 over a square root of 5 minus 4x. Okay. So can it be 0? This one can never be 0, right? Because here is a fraction, you see, and the one on the top is always fixed to be -2. It never be 0. So this one, your derivative cannot be 0. However, the thing that you may need to keep in mind is that, hey, here as a bottom, so it means that your x cannot be what? Your x cannot be 5/4. Okay, cannot be 5/4. Is that correct? Okay. However, your x is already, I mean, this 5/4 is already not in this interval, right? Because it is greater than 1. Okay, so it means that this one is okay, all right, because it is already outside the interval under consideration. So it means that your f prime x, okay, can never be 0, and it is exist, okay, for each and every x inside this closed interval. All right, so it means that there has no critical number. So, okay, there's no critical number. However, can we find the maximum and the minimum? So don't worry, it's just saying that if they have a critical number, you just find the value of that critical number comparing with those two endpoints. Okay, so if there's no critical number, you're just comparing the two endpoints. All right, so you just compare the x at the point -1 and 1. Okay, so looking at the function value at those 2 points. Okay, so if your x is -1, so you have square root of 5 minus 4 and -1, which is 5 plus 4, so square root of 9, which will be 3. And this one, if your x is 1, you have 5 minus 4, so it is a square root of 1, which is 1. So already this is a what? This is a absolute max value, right? And this one occurs at x equals to -1. Here it is the absolute min value, and this value occurs at x equals to 1. Are we all right for this function? Okay, so the maximum and the minimum just considering at the endpoints only, not at the, because we don't have a critical. Okay, how about this one, the e with the sign? Okay, so don't you worry about all the function, okay, that it look complicated. The thing that you still need to find is your f prime, right? So your f prime, it is the first derivative of the second plus the second derivative of the first, right? So you can pull out e to the x and then cosine x plus sine x. Okay, and this one again, because it is like a sine and cosine, the exponential, so it always exists, okay, for each and every x inside this closed interval from pi over 2 to pi. Okay. However, can we find the critical value that make your derivative equals to 0? So you have this one. Okay, make it equals to 0. So it means that because your e, don't forget that this one always positive. Okay, so the only thing that can have a chance to equals to 0 is this cosine plus a sine. Okay, so it means that your cosine equals to negative sine. Okay, and I mean, if your sine is not a pi, okay, or you can see that, hey, I mean, at which value that your cosine is a negative sine. Right now you are considering from here pi over 2 to pi, right? And on this one, okay, on this part of your quadrant, okay, the second quadrant, your sine is positive, right? And your cosine is negative. Okay, and when is it that your sine and cosine, I mean, attain the same value with a different sign? Okay, so it is the one with the what, with the pi over 4, right? But this one will be a pi over 4 on the second quadrant. Okay, so it will be pi minus pi over 4. Okay, or it is 3 pi over 4. All right, so this one, it is or inside this interval, is it from pi over 2 to pi? Are we okay? Okay, so it means that you need to compare the function value at the point 3 pi over 4, which is one of the critical, at the endpoint pi over 2, and at the endpoint, which is another endpoint, which is pi. Okay, so here your function value at the first one, don't forget that you need to go back to this function. Okay, the function value, so it will be what, it will be e raised to the power 3 pi over 4, and then side of 3 pi over 4, it will be just a positive value, right? And it will be as square root of 2 over 2, or you can say that it is e to the 3 pi over 4 over square root of 2. Okay, and I will use my calculator to, like, roughly speaking, calculate a little bit. Okay, it is the what, exponential of 3 pi over 4, and then over a square root of 2. Okay, and the value, it is about 7.46. Okay, how about at pi over 2? It will be e raised to the power 2, and then sine of pi over 2, and sine of pi over 2 is simply 1, so you have just e raised to the power over 2. So let's see, e raised to the power over 2, it is a what, pi over 2. Okay, let me use the calculator, and it's saying that it is about 4.81, and e raised to the power pi with sine of pi, but sine of pi is 0, so this one is not that difficult, right? So here, of course, it is a what, already the absolute minimum, right, value, and this value occurs at the endpoint x equals to pi, and this one correspond to your absolute maximum value, and it is occur, okay, at x equals to 3 pi over 4, which is the critical value inside that interval. Are we okay? All right, so we would like you to go over the exercise 4.1 number 29 to 44 and 47 to 62, and we are going to stop this video clip right now, and we will continue further with some other kind of problem, but still concerning the optimization of a function. So we'll see you then. Bye bye.